Okay, so first of all, thank you very much, Emmanuel, and all of you for the invitation. I'm very happy to be back in France after more than 10 years since I did my PhD over here. It's always a pleasure to be in France. I always pass by, but I couldn't get the time to be here. Thank you very much for the invitation. Thank you very much. So I work at the Center of Studies in Resources Engineering. This is a center, not a department, which was mainly made initially for only research purpose, no academic, no degrees. But since past 8 years, we had courses which are which we call as an MTech courses, the Master in Technology, and also the PhD program. We don't have any bachelor's program over here in the center, which is in the Institute of Institute of Technology, Bombay, which everyone knows. So it's one of the premier institutes in India. I joined over here in 2011 as an assistant professor. Now I'm an associate professor. After finishing my PhD in France from 2004 to 2007 at INRIA, Sophia Antipolis, and at Telecom Paris. And then I left for Canada, for the Canadian Centre for Remote Sensing, CCRS, in Ottawa, where I spent 3 years working with Dr. Rita Tuzi on only on SAR polarimetry. And I came back and I started this group, and I'm leading it at the moment with one more professor, senior professor, and around 5 PhD students and around 6 master students at the moment. So what I'll be presenting over here is all the work summarized mostly in what we do at our lab. So as it says that mostly we deal with polarimetric images. Sometimes also we deal with dual polarimetric data, but the group mostly deals with full polarimetric data for both on theory, on also applications, on many different Earth observation scenarios, starting from cryosphere to agriculture to urban areas. These are the three things which we are focusing on. The projects are on mainly focuses on these 3 topics, but I also work with other people who are basically mathematicians and physicists, which are for developing different kind of models. So they're more theoretical. So I'm both in this group and the other group I'm managing. So what I'll be showing over here is just a whole thing, what we do in different parts. And since I'm here for another 3 weeks or so, I'll be happy to discuss if you have any interest in one particular topic or in fact on all of them. So what we are understanding over here, most of you know remote sensing, there is nothing much to say about it, but it's just to start from the very beginning, is that what we are doing is just an interplay of the electromagnetic spectrum, is that people over here are in the optical region, multispectral and hyperspectral, some part over here in thermal from 12 micrometer to around 14 micrometer, and then we go to the region of microwave remote sensing, where people do both passive and active. We are more into the active scenarios. Limitations, where I'm not trying to say that optical data sets are bad, but there are limitations in the type of work which we do. Since we belong to a country where it is tropical, most of the time it is cloud cover, be it for agriculture, be it for the Himalayan cryosphere. It's all the time, most of the time, we see that these are all cloud cover. This is the Sentinel data series, and you can see most of the places this is for an agricultural application. And this is most of the time, it is heavily cloud cover. So there are some limitations. What we are doing over at in the technologies of radar remote sensing is we are pulsar. People do a lot of INSAR techniques over here. Then we have the newer technology coming up in pole INSAR, incorporating both polarimetry and interferometry together. There is tomography and there is pole tomosar. And the new one, which is upcoming, it is done by some people, few people in France, I know, is the pole time SAR. This is the newer thing which is coming up. This is very interesting because all of them, you can apply the pulsar into all of them together. Well, it becomes more complicated when you move into this thing, but it also requires a lot of data sets. So these are all coming up with newer missions, but this is all the technology which are there. In our case, at the moment, we are only looking into either agriculture or cryosphere or the urban area studies. In the near future, we can expand into more forestry and so on. At the moment, we are not doing it because it's just that we don't have data sets available and we do not have any kind of collaborative projects which are going on. But at the moment, we are mostly into agriculture, cryosphere, and urban area studies. In this talk, I'll be only concentrating on the pulsar studies which we do at large at our center in our group. Now, I define radar polarimetry in this format. If we understand all these three circles enough to do SAR polarimetry. This is not my original idea. This is an idea and a discussion with Professor Avik Bhattacharya. This is actually his idea, which I just made it into a little bit more variety way. But actually, he was the one which was the idea when he was doing his PhD, and then it all evolved kind of thing. So either we do physics, statistics, and there's a common link of geometry. If you just do a physics and a geometry, we are in this polarization geometry, which I'll be talking today. And also, if you are in this area, you are in information geometry, which there are many people who are working. There are less people over here, but there a lot of work going on in also in information geometry. I did a small amount of work over here, but we are mostly over here is to mix physics and kind of geometry along with statistics to get this polarization geometry part. Now, just to give just a little bit more, give an idea of what we are doing over here, just to leave not too much of mathematics over here, is just in pulsar data, which we are trying to see is that we have an incident electromagnetic wave, which is in component AX and Y, the polarization. Polarization is nothing but the locus of the electric field as it moves in the space, which is transformed by this matrix, and this is the one which you get scattered one. So everything relies on what you have over here in this 2 cross 2 complex matrix, which is this S matrix, known as the scattering matrix, which contains the information about the change of polarization between the incident and the scattered, where you transmit an X and you receive an X. You transmit an X polarization, receive an Y, the cross one, similar over here, and the other one. So it's just 2 cross 2, where it is in an amplitude and a phase information. That's it. This is dependent on the scatterer shape, material, dielectric, moisture content, many other electrical properties, the frequency of the EM wave, the geometry of the target, and coordinate system in which you are measuring it. So it contains all this information inside them, coupled in a very complex way. The idea is to how can you retrieve this information in whatever applications in which you are interested in. So at the end, what we get is just this matrix, which is just called the absolute scattering matrix. But you can just take out an absolute phase factor, which is out of this, and you have the relative phase matrix, scattering matrix over here with 4 amplitudes over here and 3 phases. This is the most general case. This is the case where it's called as a bistatic. You have a sensor which is sending your electromagnetic wave in certain polarization that is measured in some other framing. This is the most general form, but we don't have this actually in practice, but we have in monostatic. The sender and the receiver are the same place. In that case, this and this become same. So xy is the same as pi x. So it actually boils down to 3 amplitude and 2 phases. So the total number of scattering or parameters which are enough to characterize a target is 5. This is the golden number in SAR polarimetry. That's it. What we don't use is this one, which is the absolute phase outside, and this is the thing which is used by people in INSAR. This is the phase which is used by INSAR. The rest is all what we use for pulsar. This is what is the total information which is the starting point of SAR polarimetry. But life is not so simple as such, and we have more complications. If everything would have been such nice, perfectly polarized, everything well scattered, everything is fine, then the S matrix would have been enough to do our study. But it doesn't happen. Nature is like this, where you have complex scattering. When you have this complex scattering, the scenario is that you have the polarization all not in a very proper format. Things are partially polarized. Nothing is completely polarized. In that case, S is not the one to be working with, because this doesn't contains the coherent information. Because SAR, radar systems, are our coherent system, like any other, like ultrasound and so on. This is okay when we have the coherent measurement, but as soon as we have starting to have partial polarization, we need to check over here. Now what we can do is, from here we can give a statistical description of the measurement and the information, and from there we start another path to do a polarimetric analysis. We can either use this if everything is fine, deterministic, but if it is partially polarized, non-deterministic cases, statistical description. How do we do that? Don't have to go to the mathematics of it, but it's very simple, is that in a deterministic case, we have the S matrix. We just go to find out a vector. There's nothing but a vectorization of a matrix. Can be done in various possible ways, not only one. The various possible ways of vectorizing a scattering matrix with some basis matrices, that's fine. And at the end, what you get is this statistical description is an ensemble average of nothing but kind of an outer product of this. This is simple as that, where you have the three diagonal elements to be as real and the off diagonals are complex in nature. This is what is called in the literature as the coherency matrix, but it is actually a covariance matrix. But it's just to differentiate between different kind of bases. It's just a name is given as a coherence, but it's actually all of them are covariance matrices. The next one, if you see, is what is called as a covariance matrix in the literature of Pulsar. Is nothing but just the basis is changed. Before, the basis was something different, which is called as the Pauli basis. It comes from actually quantum mechanics, just borrowed over here, but actually it's nothing but the simple case of doing it from a complex algebra. But if you just go to the other basis, which is nothing but lexicographic, you get another matrix which is called a C. So you get a T over here and a C over here, where both of them are covariance in nature. But the question over here arises is that why do we need two of them if both of them are covariances? It's just that if you go beyond before, when you are doing coherency, this vector, each element of them actually relates to a physical scattering mechanism. That's the beauty of it, because it has been borrowed from quantum mechanics, and if you just use them, this quantity, and this quantity, three of them actually characterizes a scattering mechanism. That's why this is important. Whereas if you go to the covariance matrix, they change over here. They do not relate directly to a scattering mechanism, but they are something like a system property. So either you are in the system or in the scattering. It's just that. But they all can be changed one to the other with just a unitary transformation, because they have this property. You can go from a C to a T and a T to a C just by doing a unitary transformation from each other. That's it. It's very simple as that. So in whole, we have guess going from here with a bridge over here is a vectorization to either a coherency matrix or a covariance matrix utilizing this kind of an outer product. But there is another quantity which is very important, has been less used in literature, has been taught by many, by Professor Avik Bhattacharya and Shane Cloud and so on, which is called as the Kenyu matrix by Professor Kenyu, who was actually turned the electromagnetic theory from there to radar remote sensing point of view. He was the one who actually diverged it into the field of radar remote sensing, is this matrix, which is the Kenyu matrix. It can come from there. The beauty of them is that all the quantities over there are real quantities. It's easier sometimes to work, of course, with real quantities, not with this thing where you have complex quantities over here. Only the diagonals are real, but the off diagonals are again complex. So it's sometimes become a bit cumbersome in trying to analyze them. But here, everything is now real quantities. All the 16 elements over here are real. This is the Kenyu matrix, which has been less used in the literature of Pulsar. This is the diagram as we given by Professor Shane Cloud, is that you can go from one to the other. It's not very difficult. It's very, very simple to go one from the other. You can go from there to here, here to here, here to here, and from here to here also. But there are some red lines over here which shows restriction, because since you have come from here to here by an averaging, which is still nothing but a spatial averaging in this case, the the rank of the matrix has changed. So this is now become a full rank where you cannot go again back to a deterministic target. It's not possible because you don't know you have averaged it. You cannot go back to a target. So in this case, these are all restricted entries. Some point maybe yes, you can do that, but not always. So this is the way you can represent pulsar data, either by a covariance matrix C, either by a coherency, or the Kenny. In all of this talk, I will be only concentrating over here on Kenny because the model which I will talking about will be all made by this Kenny matrix, which is a 4x4 real matrix. Now, this is just a representation. If I have a coherent target, then I only have the S. I can go by just a Kronecker product. I can just get the K, which is nothing but the A is nothing but a projection matrix. This is a 4x4 real. But if I have an incoherent, as I said before, you can go from a K. It can be written in terms of the elements of the coherency matrix. It's simple. You can see all of them are real quantities over here. It's very simple to find out. Nothing very difficult. Nothing very great over here. So we are not doing anything great, but it is just that we are trying to bring things together which are there in the pulsar literature. Why is that? So what I do is now I try to see that there is a geometry which is defined on this space of the pulsar data. And utilizing this, we define a geodesic distance. It's nothing but the great circle on a sphere. And if you see that, we can easily find out this geodesic distance as simply nothing but utilizing the Kenny matrix. It just gives you a geodesic distance, the distance measure only. But we can simply imagine this to be in a 16-dimension space because this is all of them can be vector of 16 dimension. You can just open the matrix, 16-dimension vector. So you can imagine that to be a 16-dimension space, but just to difficult to visualize. But this is just a quantity which is a geodesic distance, which is between 0 and 1. Now, why this is important? This is scale invariant because I'm not dependent on any scaling, and it is also rotation invariant and so on and so forth. This has very good physical properties. The idea is, can I utilize this for various applications or not? And this is where was the starting point with this paper which came out in 2017 along with Professor Freddy and my students and other people, and we gave different applications just by utilizing this. And it turns out to be that this simple quantity can be used in different forms for various different applications. And this is what I'll be showing in my presentation over here, just the utilization of this quantity, which is nothing but a geometrical form of representing pulsar data, which has not been done before in the literature. What I'll be talking about is the 6 points over here. Change analysis, everyone knows over here, even also image clustering. Radar built-up index is that if you go into optical remote sensing multispectral, people define many kind of indices like NDVI. NDVI is a very common index for meditation. But there are many other indices which are utilized in different bands of a multispectral to find out built-up areas. All depend upon the reflectance pattern. But there is nothing has been given in the domain of radar utilizing full polarimetric data. And we gave this one as a radar built-up index. We'll show what exactly it is. The next one is the radar weightation index. Weightation index, as I said before, the NDVI in multispectral is widely used. Everyone uses the NDVI. There is one weightation index in radar also given by Professor Jakob van Zyl from JPL NASA around 5 years ago. It was simple to compute, but there are many limitations out there. It was not utilized a lot in literature. Because maybe there was only 2 papers, that's it. Because people did not use it much because they found out that there are too many limitations out there utilizing that. So we came up with a new weightation index, which we call the radar weightation index, but there's a G which is nothing but just called a generalized volume. We'll talk about that later on. Then there are these new parameters which are role invariant. Now what does role invariant mean? Because radar, remote sensing being a side-looking business, the radars looking as a side edge, and it can have more of tilt and orientation. Now due to that, you can have a same target giving a different kind of signature if it is oriented to the radar line of sight. This is what we do not want, because the target should be same even if you have rotation. So it will be rotation invariant. This has been given in literature by Professor Potier and Shen Cloud using different kind of parameters which are role invariant. The Cloud Potier scattering parameters and entropy and many others, which are role invariant because they only depend upon the eigenvalues of the matrices, which are again role invariant. We also came up with something new, but just utilizing this geodesic distance point of view, geometry, nothing else. We came up with 3 parameters over here. I'll talk about them, what they are. Then we came up with something which is called the scattering power factorization. In literature, if you see, there are people coming up every day with a new decomposition, which they call as scattering power decomposition. Changing some of the models here and there, you can have different kind of decomposition. What we did over here is that to remove that decomposition kind of thing, because there are again a lot of restrictions in choosing the model, utilizing them, and so on and so forth, we gave something which is called as a factorization framework. Not a decomposition as such in the nomenclature of SAR, but a factorization framework. We'll see all of them. Chain analysis, as we see that we are doing this analysis over the data sets which are PolSAR, InSAR, and PolInSAR, and so on. We are doing it over here as Pol times SAR. Why it is so important? Because now for Pol times SAR, we have newer system coming up. From the ALOS PulsAR was 46 days, but the ALOS 2 is 14 days only. And there are several of them coming up. SAOCOM being the Argentinian one, will have the 1A plus 1B as 8 days. So you will have a lot of repeated kind of data, and you can try to analyze them, the time series of them in a very nice way. Not only that, you can also see the evolve of the scattering of the parameters, which are polarimetric parameters. This is what we have. This is for a snow cover. I'll not talk about a snow cover over here. Keep it for the 11th, which is talk about more of the snow cover. So the snow cover analysis over the Himalayas areas in terms of the full polarimetric images, which is in the month of February, where you have a lot of snowfall over here. It's this being around 2,500 meters to 3,000 meters over here, around. Over here, this is the city of Manali, a very touristic place, and this goes up over here. These are all very high mountains. The tree line over here is just over here, and then after that there is no tree line over here. It's all rugged terrain. If you see, it's all heavily snow-covered areas over here in the month of February, in the month of March, and as soon as you go in the month of August, it changes. It's the full PolSAR image. It changes, everything becomes surface-like. The snow has melted over here. The next beauty is, I'll show that in maybe on 11 now, but is that you see over here, this is the forest. This area up to here is the forest. But the forest shows blue. It's not very clear why it is. Why should a forest show kind of a blue? Means something like a surface scattering. This goes over here and goes back. Because the forest is frozen. It's a frozen kind of a forest. And you can clearly see that this actually shows a lot of surface scattering, and as soon as you go to the August, you see everything is gone. Now you have leaves which are now not frozen, and you start getting something like a volumetric scattering. It was interesting to see that phenomena. Initially, I thought I was doing something wrong, but then we had collaboration, and we saw with people who are actually working over there, and they told us this is actually what's happening over there. We'll talk about that in other presentation. This is over here for urban area. This is the area. This is an image from the UAV SAR. It's the bitemporal change from 2009 to 2015. Changes over many urban areas have come up over here. This is just a change map, but this is done with some machine learning techniques. This is one where Davide is one of them, was to do the Vancouver change, urban area changes for many different cases, which was there by my student and Davide, along with Lorenzo, on something on deep learning, using full polarimetric SAR data on time series analysis. This is for a land cover change analysis for vegetation. This is the multi-temporal every SAR data, the ESAR campaign from DLR. And if you see, there's a lot of change in many places of vegetation. From here to here, this was wheat. Over here, it's all harvested. Clear. There's nothing over here. So over here, it was when it was wheat, that the polarimetric information was something different. But when you come over here, it changes. So this is what we can see in many types of land cover, snow analysis, and urban analysis for pulsar data. We just see one for an urban area. What we do is nothing but we just try to see them is not indirectly changing, but into change in the scattering mechanism. How the change is happening in terms of either a trihedral scattering mechanism, which means that's a surface. Trihedral is a similar as a surface kind of scattering. Dihedral means it's something like this wall over here. It comes over here, hit and go back. So it's a two bounce scattering. Surface trihedral over here is a single bounce. So an odd bounce and an even bounce. And I take this one as a dihedral, which is 45 degree rotated. It means I have a dihedral like this wall, but if I orient it with a radar line of sight by 45 degree, it gives only cross polarization, no copolarization. That means it's this structure, just because it has been moved away from the radar line of sight, has given me cross polarization. So this is the three thing which was in the idea which was long back, around 3 years ago. Just take three of them, convert them into this K matrix, the K-nu one, which is just simple, doesn't matter at all. But it's very, very simple, and to see how they are changing with respect to each and every scattering, not the global change, but the changes according to the scattering. Because otherwise people just say, okay, it has changed. What has changed is to understand it. So with utilizing them, we just found out the trihedral change using the geodesic distance. The geodesic distance at time t1 between the observed matrix, the observed one pixel, to the one which is the trihedral minus at t2 the same. Similarly for all of them. And what is the difference image at the end is nothing but the maximization of the geodesic distance. The one which is maximizing that is the one which is the difference image over here. This is what is there. So it takes a patch of image in which David and others they have worked on when this ground truth was available. Is that this one with this one is a change. You can see this one marked. This is the ground truth map, and this is the Google Earth image as it looked like. If you try to see the change between the 2000 and 2015, you can see the changes using the geodesic distance. Just the distance measurement using the K-nu matrix, simple as that. If you want to see, this is utilizing the full pole information. I take the full polarimetric information and I do it. But it might happen sometimes that as we have now Sentinel, we just have a dual pole. We don't have the full information. Can we utilize it? Yes, we can. We can just take the HHVV. This is something like what we have as TerraSAR-X. They have this one. If I see that it's not as good as maybe the full pole, if you just do it quantitatively, but not bad either. If I try to see the change map, just to threshold it with this is the ground truth, well, it's close enough. Not maybe appropriate, but close enough. What happens if I take the HH and the HV? I don't have the full pole. I have something like a Sentinel, HH-HV. It's not good at all. It doesn't capture the information. The scattering information from an urban area is not captured because I do not have the full polarimetric image. It's very bad. Similarly, if I have the VVVH, that means I really have to be careful if I am using the dual pole scenario in this context. It doesn't work, but it's not true again because this works. Just because this is very rare, it is only with TerraSAR-X. No other system has this kind of thing. Only TerraSAR-X have this HH and VV mode. All other dual pole and upcoming missions, they have this kind of thing, which doesn't actually work very well. So full pole fine, dual HH-VV is fine. If I try to see what happens, as I said, now I want to see particularly to a characteristic. If I want to see what is the change which has happened in 2009 between the image and a dihedral, I see that the changes are over here. It is these things are not there. This was not built up. But if I just see over here, it has come up. So clearly shows me that there is a dihedral change from here to there, which is very nice because otherwise every places it is almost close to zero. Over here, this is something very high. The change over here is an only dihedral mechanism here and here. This was no built up, it was built up in 2015. So not only we are trying to see a global change, there was something, there is nothing, but also to see between mechanisms, which is very, very important. I'll show you a very beautiful example, not over there on the other presentation which I have for snow. It can be really, really nice characterized with some kind of a scatterer for fresh snow which is there, and then you have no snow at all. It looks very, very interesting. But we save it for the other presentation. This is for the urban one only. If I just see it over on all of them, utilizing our methodology, is that if we just have an HH only an amplitude, this is just a ratio kind of thing. If we just use an HH amplitude and see the change between the two of them, this is the thing, HV, VV, the total span is the total power, nothing. But if we see the GD, which takes into account not the power, but it takes into account the polarimetric information, it is much better in many sense. But the HV is also better with the kappa, but doesn't matter so much over here, but at least you have a better way of change doing detection using the full polarimetric information with our geodesic distance measurement. Clustering, we utilize the same, again the same thing over here, but here we construct a similarity measure. We have the geodesic distance, from the distance we just do and 1 minus GD, a similarity. It's better to use sometimes a similarity measurement than a distance measure. We just normalize it. Fi divided by all the Fi which you can have. And if we just use a trihedral, a dihedral, and a random volume. This is, for example, saying that in a space, I have smaller kind of dipoles over here, like this, and these are oriented in any possible ways. I take them and I integrate it over an entire volume. What I get is something like that. I mean, if you do it, it's not very difficult to do that. So it is nothing but if you do that as a random volume, dipole in a volume, integrate over the entire volume space, you get this random volume. So I get 3 scattering mechanism, a trihedral, which is surface, single bounce or odd bounce, you can say to be very clear. Dihedral, which is double bounce or an even bounce case, and this is totally random case. So 3 distinct cases I have taken. If you see how you get the similarity measure, this is an image of an SAR image, the Pauli RGB of San Francisco area in USA. Pauli RGB takes into account, the text says that the blue is a surface because it's just a water body. Here the area B and A, these are urban areas. And these are the areas which are kind of parks and something over here. This is the park and so on. So it gives you nothing but a green, which is a volumetric. These are scattering by trees and whatever it is. But if you see over here, in this, it is not very clear because these are very densely urban areas. And also the satellite is flying this way and looking at this way. This is the way. It is flying in this way and looking at this way. So the urban areas over here are proper urban areas, but they are slightly tilted to the radar line of sight, and they are also in an altitude. If you go from here to there, it is around 120 or 140 meters difference is there, this area. This can be seen in Hollywood movies where you can see these cars are going like this and this. This is these areas. They are all very undulated. And because of this undulation also, radar sees that there is more cross polarization than the copolarization because of the undulation, because it all depends upon the radar line of sight. So it looks that it is over here an area of urban, but it's a bit confusing because it is a bit greenish. Then it should be red because R corresponds to the one which is double bounce or even bounce. The blue corresponds to the one which is more surface. The green corresponds to one which is more volumetric. So it's RGB. But if I do and we see that over here when you do a trihedral similarity, the water bodies of course is very high because this is corresponding to that is a trihedral. It's a odd bounce scattering. If you come over here as a dihedral, this one goes to 0 because this is all trihedral. It is just the opposite. But over here you have more of urban areas which is higher over here. If you go to the volume, this is more volume because as it's over the parts areas are more volume. So this is able to capture each one of them separately, which is not possible over here. Now, you can see that very well. I can take something of them and I can make those kind of fraction number of total number of pixels, and you can see it is ours is the GD1 is much more higher in areas which are actually corresponding to a double bound scattering, which is actually urban area, compared to the one which is given in literature. Don't have to bother about what they are, but just literature it says this is the green, ours is maximum, and since there is no volume, odd is of course not there. So it is able to characterize much better than what is there in literature. I'll not go to the thing because it is already there in literature. Is given by Professor Zhongseng Li. We just replaced it by our own, and you can see in this paper it is there. We have replaced it by this one, and if you see, this is the one given by Zhongseng Li, and this is the one of ours. This is to say that I have made segments of some odd bounces, maybe 1, 2, 3, 4, 5 in the volume also 5, and so we have just made them more segments out of each one of them. And if you see a more closer look, zoom look, you see it is much more better over here as urban compared to what given by Professor Lee. So it's able to characterize more if we try to find out the similarity measure using the geodesic distance rather than just taking the one which is given in the literature, and just this is nothing but just taking them and just doing a Wishart classification. Simple as that. This is our area of Mumbai. This image is upside down because the last two images are taken in a different direction. But this is area of Mumbai. You'll see in a different plot better. This is the same thing we have done with the Mumbai, all of them, and it shows much better classification. I'll just go fast because the same thing over here is done with Professor Lee's method, and our method is much better in doing the clustering process. The radar built-up index is done by our collaborators are from the University of Federal Alagoas, Professor Alejandro Freddy and Professor Paulo Gamba from the University of Pavia. We're all collaborators in this work to make our radar built-up index. This is nothing but I'll just quickly go into the thing is that we try to find out that given a measurement, 1 pixel corresponds to this observed. Now, what I do, I take this observed and I take all the models which are available in literature. I try to take this one and I try to rotate them, just nothing but an Euler rotation, and to see it's matching which one of them closer. The one which matches closer to that, I take that angle and I rotate all of them, because that's the maximal similarity. This is called, it is called in literature, design to the maximal similarity. I'm trying to make it which one it is maximum to. Then accordingly I find out the similarity measure. It's nothing but, as I said, it is 1 minus the distance. I sort them to find out which is the dominance one. And I take the condition that if the first 3 belongs to either a dihedral scattering or a narrow dihedral or a helix, I know this is a built-up pixel, otherwise it's not a built-up pixel. This criteria comes from literature because no one has given them sparsely in many different things, but not together. The other one is just I make this one as the radar urban index, nothing but the maximization of all the similarity measures between the dihedral, the narrow dihedral, and the 2 helixes. Helix is there is no such scatterer in nature called as helix. Helix is something which transforms a linearly polarized wave into circular. That means it is something like it's an asymmetric scattering. I'm having a linear polarization. There is a target, there exists a target or a combination of targets in a resolution cell which will take this linear one and put it into a circular. That means it's making the thing more asymmetric. And it corresponds to the area, in urban area it happens more because of the structure. The structure are in such a way that it's possible that you have in one resolution cell building facades which are in some combination of lambdas of the wavelength. There's a resonance and it changes the polarization. That happens maximally in urban areas. You'll otherwise find no helixes anywhere over there. And this is what we have taken over there. If it's an helix component, it will be very low in fact, but still it corresponds to an urban area. And we have taken this one as a thresholding, just doing an Orsud kind of thresholding to see if it's built up or a non-built up area. If you see, this is the area, this is the San Francisco area of USA. It's a radar set 2 image. This is the same, all of them are urban area. If you see, this is the dominant scattering band. The first dominant corresponds to all of them urban area. And this is the one which is the radar built up index. That means the more higher it is, the more built up it is. That means, of course, here there is nothing, zero. And if you just take them and just do the dominant sorting or the thresholding, either of them, there are two methods together you can use, you find the urban area. It is very, very interesting to see, if you have not seen before, is that this area is actually an urban area. It's just that that's why these images are very much used in radar polarimetry to test one's algorithm. The flight is from here to there, and it looks at this direction. Everything is fine. These are all urban areas over here, very dense. This is also an urban area. But just that it is so severely rotated, it looks like something like a vegetation, because of just being rotated to the radar line of sight. It's just almost 45. And this is very critical, because you can never know algorithm you can apply over here to extract this to get, or you just take anything and classify it. You can never classify this to be an urban area. This is always a problem. People have been fighting it for years to make that. The good point over here is there is no assumption. People, what they do a clever trick I've seen, is that they say, when they do a supervised classification, they take some samples from here, samples from here, samples from here, and say this is urban. And they take something from here and say it is rotated urban. Well, there's another class, of course, fine, it is okay, but it doesn't solve the problem. It's a kind of a trick. But here we did nothing at all. It is totally unsupervised. Still, we are able to somehow capture this, which is okay for us, because you cannot do that with any possible methodology to find out that kind of an area. No possible, because the electromagnetic scattering doesn't allow you to do anything over there to make it as an urban area. So this is the area of Kyoto, Japan. It's very heavily urbanized area. This is all very thick forest. Over here, the radar set 2 image. You see again, the first scattering is from urban area. This is the urban area index. And this is again the urban map. The question comes is, then how do I validate it? Well, it's difficult to validate it. So what we did along with Professor Gamba is that it was validated with, there is something called a global urban footprint made by DLR, with one with 80-meter resolution, one with a 12-meter resolution. It's for the whole global one. You can see that for free. You can download that also. It's beautifully done. Fantastic work they have done with the product. It's called a global urban footprint product. So he has taken them and tried to see whether how much it is matching. It's very, very close to the 12-meter. We have projected them into 12-meter again, and we have seen that it's close enough to what they have done. Okay, of course, there is much better, of course, in that sense, because they are using multi-source data sets to make that map. But here it is just one sensor and just one algorithm over here. They have used many different kind of things to find out that. This is the area of our place, Mumbai. This is where I come from. These three lakes are there. It's IIT somewhere here, over here. So it's all very, very heavily, densely populated. It's impossible to find a place where you don't have a building. It's impossible. These areas are all central part of Mumbai, and it goes up to here, this is the sea, the Arabian Sea. Over here, and this goes to the south of this is the entire place is Mumbai. This is the newer part of Mumbai. This part is national forest in between. It's very green, this national forest, and so we are just on the side of it, so we are also very green over there. So it's just the urban. If you see, this is the urban area which I've captured with our work, and this is all the urban area from our. This is one of the results from the UAV SAR from LA. This is a built up again dominance. This is very, very well extracted over here by the dominance map. This is a Pavia. This is the whole of Pavia, but Pavia is very difficult to get over here because these all of them are kind of spread and they're all possible and all possible orientation and very dense in between. The center is very, very dense over here. You see, it's looking like as if it's a green kind of thing. These are all nice over here, so that they are all nicely done, but in the middle it's not so good, but still it's okay for the first instant case of finding out urban area. The vegetation index is what we are also, we are working also with Alejandro over here, and a major part is we are having a collaboration with the Agriculture and Agri-Food Canada under a scheme which is called JCAMP, the joint campaign from going on with 20 different countries. Most of the European countries are there, and India we are there, and with Canada and other places. The idea is to see again the time series of this is under this MapVex dataset, soil moisture active passive experimental, which was done in 60 in Manitoba. The datasets are not free, but we got them just for them from all the stages of the growth of plants over here. It's from 30th May to August over here. What we do over here, just to give an idea that what we do in our group is that we do all the agricultural application, is all these things. So now we are mostly into these two, crop classification and biophysical parameter estimation. And the idea is to give something like an whatever the ready product is in terms of PAI and biomass and so on. Soil moisture is also a part of our work. Phenology estimation. We are working with phenology estimation along with Professor Juan Lopez Sanchez from the University of Alicante, Spain. He is one of the best possible. So here we are doing this analysis. This is not yet done. Soil moisture and of phenology using full polarimetric SAR data. This is what we show is what is called as the radar vegetation index. So if you see initially on 35 May, nothing was sown. Everything was bare ground. So the radar vegetation index is very, very low. It's almost zero. But with time, you can see the temporal increase in the radar vegetation index, how it's increasing, and it's increasing the peak growth stage in July, and then it starts to dry down over there. And some of them are harvested. Some fields are harvested, not all of them. So they harvest not at the same time, but few fields are. For example, you see those blue in between, they're all harvested field. So everything is gone. And some of them are dried down crops also. So you can see the evolve of them over here. And we just compared it or just with the PAI, the plant area index, along with the vegetation index. It nicely follows, is better correlated than the one given by Jacob Van Zyl, which is this RVI. Ours is much, much better correlated over here. Similarly with the volumetric water content also, it's better than, of course, than the one. This is a very, very interesting to see that we are doing much better, and also the characteristics is much well captured in the time series. That's very, very good. And all of them are done again in the geodesic distance framework. I'm not showing how the computation is. It's a bit complicated, but you can see the paper over here is what we have it at GRSL IEEE. So this is again a nice way to see the evolve of all these crop classes for different. We are now analyzing it for different crop because for all the crops now we are doing it for different crop stages. If you see, this one is very interesting. This is the analysis I did very recently. This is a 2018 data, all given by our partner from Canada. This is an area in the south of India, very south of India, where India being a very large production of rice, it's very important for us to always focus on some kind of rice cultivation over here. This is an area which is a lot of rice cultivation. This part of the river is also, there is a rice cultivation on the other part, but they are done in a different way. One is seeded, the other is transplanted, and so on. So I mean, I do not know much about it. I'm not an agricultural engineer, but I just work with them, so I know the words basically. But these are all areas which are rice planted. At this stage of the year, there is no rise. This is only when they put water, just that's it. And you can see it's the GRVI and the RVI, both of them are very low values. Nothing is there. Here there is some amount of roughness. Rice has not come off, right? Just the fields are plowed. So it is a bit roughness, but this is not due to rice. Now, as you see, as you move on and on, here rice comes up. And rice shows something in the poly RGB image. Rice shows very red. Red means something like an even bounce scattering. Now, why should rice show a lot amount of even bounce scattering as if urban area? Because here there are these straight things are there, the straight rice, and everything is water beneath. So the electromagnetic wave strikes like a mirror on the water, and there's a strong double bounce along with the rice. Always rice fields with water shows a high amount of double bounce, and this is a problem which has happened with an RVI. Now if you see, as here it is fine, but as rice comes over here showing this kind of double bounce, you will see it is more double bounce over here. Here is more water than here. RVI still shows nothing. It still fails. But ours started to show. This area started to be rice over here. It again fails, as if this is the same thing it's showing, all of them. But here you see the dynamic change over here. Now see the drastic change that it happens. After 20 to 8, you see everything becomes red. This is all temporal series, I'm saying, and it's beautiful. You see everything over here now, it is all peak rice season. Still you see nothing over here, as if nothing has happened. But ours is again able to show these changes, because the way we modeled it is very different from the way they have done. That's why people have not used RVI specifically for rice, because of this problem. But this is all rice, and at the end of 26/11 when you have in November, this area is harvested, but here still rice is there. Now as soon as rice, it's also some part is harvested. Here as rice is harvested, the fields are just taken off and the fields are like very rough and random. In that case it shows something, but this is because of the roughness of the soil. But this is not what we want. RVI should be meant for understanding the characteristic when the vegetation is there, not when the vegetation is gone. We show the same thing over here, but here it starts showing when the roughness comes into picture. Whereas when there was standing crop of rice, it shows nothing. So this is very, very interesting result which we had, and you can see that how it is the dynamically changing with this crop, as from 35 to 6 June to July and to August. So beautifully it shows all aspects of how these changes are, where different kind of crops are there, wheat, corn, canola, so forth, for this data sets which we have from Canada. This paper has been recently accepted in letters, and we have another one going in inter-transaction. The role invariant parameter that I said is that we have something which is called as a scattering type, which is given by Professor Eric Potier long back, but we do on the same line. I will show how they're same line. This is scattering type. Type means what kind of scattering it is. Is it the even bounce scattering, or it is the odd bounce, or anything else? So I'm just characterizing that scattering by this quantity. It goes from 0 to 90. Towards 0 means everything is surface or an odd bounce scattering. Towards 90 it is something like an even bounce scattering. In between, there is a change of surface to the double bounce with some kind of volumetric scattering. Purity is how much the scattering is pure. Is it purely surface, or it is purely double bounce, or so on and so forth. So it characterizes the purity of the type. The next one is the helicity. As we have seen, the helix component. It talks about how much is the scattering asymmetric or not. These three quantities are again derived from the GD. Very simple, it's just one line to do, nothing else. What it does, it just computes the geodesic distance between the canoe, the observed pixel, and the one which corresponds to the trihedral or the trihedral scattering. That's it, nothing else. This is taken from work which is given in actually ellipsometry, the physics of polarization, and we have modified them in our way using the geodesic distance. This is using the left helix and the right helix together. I'll just show you more example and some images to see. This is an area again of San Francisco of radar set 2. This is the alpha of Cloud and Potier. It's the dynamic variability is very low. Here, this is urban area. Here you have a little bit of vegetation. This area looks like vegetation, but it is actually not, because this area at this time of the year when this image was captured was actually rugged terrain with very, very dry vegetation. But the area is very undulating and tilted. Again, as I said before, the radar sees undulation also as there's a cross polarization. So it looks over here as if there's something little bit like over here which corresponds to like a volumetric scattering, but it is not. If you see ours, the urban area is much more prominent. And if you see other areas, the water, of course, is very low because the water is and dominantly odd bounce. That means you have water, but this kind of water is what you say is there is a blank scattering. The waves, there are some capillary waves. So the wave is not like a mirror, it goes back, but you have a very small amount of return to the back to the sensor. Maximum goes away. Because if it goes totally away, then you have black. Nothing is coming out. So this is where you have the type. This is the purity. That means if you see the red is being more pure. So you have a blue over here. This is very much a purer odd bound scattering, which is shown up over here. Other areas are a little bit of mixture. The helicity, this is the one from the 2Z, the modulus of the helicity over here, because it's similar to ours. But if you see, it is nothing can be seen because, as I said, helicity is very, very low in most of the scattering cases. Only in the urban area you might see something, but it's too low in terms of contrast. But it scales to 0 to 45. So we have scaled to 0 to 45 in the literature. So if you do just a segmentation, as you have the H alpha segmentation in literature, you can do the same segmentation over here. If you do segmentation with the scattering alpha and the purity with just 8 classes. So 0.5 you make one, and between 30 and 40 you make another class which is nothing but the one coming from the volumetric classes. You segment that into 8 classes from here. This is how it is segmented without any prior knowledge. Just compute from the data and just put them in over here. Nothing else. No prior information, no training areas, nothing at all. Just simple from just the computation from the parameters from the polarimetric SAR data. If you see this is another image of the same area but from LOS to an L band. That was a C band image. If you see the alpha, it's slightly different because the water looks much more rougher in the sense over here because it's an L band. This is our alpha GD, which is much more contrasting than this one because the urban area doesn't seem over here. If you see the purity, again the similar way, the water is much more purer. Helicity, again, this is very dark because it's very, very low values. Similarly over here, its values are very low. If you put them again into this segmentation, it's well segmented because these areas are also urban areas actually, if you see. But again, the problem again over here is that these areas over here are again heavily oriented to the radar line of sight. The radar is flying here and looking at that section. These are all okay, but this is again a problem with the orientation. It's very, very sensitive to this kind of orientation. But since ours is a role invariant, it should not depend upon the role. It captures very well the urban areas over here, which is in this class, some 7, these classes over here. If you see, this is an area of this Mumbai. It's an LOS2 L band over Mumbai. This is what you have in the alpha. Award is capturing better the urban area. Similarly, the purity, this is again very well captured the urban area totally over here. Simple segmentation, no nothing, no information at all, only the information of PGD over here. This is an agricultural area of over Canada. This is our alpha. You see over here, this is the classification. It's classified different types of crops which are standing over there in different kind of classes. So it's very, very, because this, for this that we have the ground truth mostly, most part, so that we know what's happening over here. This is very interesting to see now. It's snow now. This is the area of Manali Dhundi. So Manali is a city which is just cut over here. This is the area. It's a very beautiful hill station in India. People come from a long places over here, and from here you go up and up. So there are 3 stations over here, automatic weather station, which are managed by the defense organization over here. 3 of them are maintained over here, here, and here. So Manali Dhundi area is somewhere over here. It's over here. These are all very, very high mountain, over around 4,000 meters high. This over till here it is 2,500 over here. So you can see this is an area. This is an image of February. Yes, the image of February where it is heavily snow covered. All the areas, this is a peak. This is a peak over here, high peak. Everything is over here is very rugged and totally snow covered over here. If you see over here, this is well captured over here. That if you now, as I said before, that this area is area which is the vegetation. This is the forested area, as I said, which was actually frozen. And if you see, it sees over here that there is this gives you surface scattering. It doesn't give you volume, even if it's a forest. And that's a very interesting result which we got, and it was very nice finding that this area, if I go, I do not have over here, I can show you. If you go now to the summer image, this area now turns over here in 40/50, which means volume. So it's actually the temperature has increased, and it's not anymore frozen. Now you have those the leaves and everything, which makes it more volumetric. So this is all snow covered areas over here. Well, some of them are like, of course, it is here. It is, we have not made the layover shadow map over here, but some of the areas are layover, and of course shadows are there. If you see again with the purity, well, nothing is very pure over here, except over here you can see some purity, but otherwise you see that it's not anything pure, because over here, as I said, it was snow covered over here, but the scattering was showing something over here. The scattering was showing something, but this is not a pure scattering, because anyway this is all very fresh snow. And this is a C-band radar. The image is acquired in the morning at around 6:15 a.m. So the previous night you have, the previous day you have like sun, so the ice, the snow has melted, and then you have the again refrozen in the night. The temperature goes again sub-zero. It is again refrozen and a snowfall. So it's like you have a lot of fresh snowfall, where you can have the C-band at least going some to the snow and giving rise to a volumetric. In the evening past, it will be something very different, because the snow will be melting, because there is a lot of sun over here also. If you see again, this is you have kind of a segmentation map over this area. The factorization is the last one. The framework is very simple in this case, but it doesn't say, as I said, decomposition, because here same thing. I'm not doing anything different over here. Again, I'm taking the observed Canyon matrix. That means for each pixel wise, I'm doing a design to maximum similarity. I'm finding out the similarity over here. But what I'm doing is now I'm finding out a convex weights out of it. Similarity, the first one is a similarity, but the next one is the similarity multiplied by the dissimilarity of the other one. So it just goes on as a product form. So the same thing, I'm just going over here, model selecting, scattering, there's nothing. So if I just do it for a coherent target, for single loop image, which means coherent target, these are all ships. The last two image, these are all ship in an ocean, and these are very nicely found out by the dominant target as being dihedral target. This is the second dominant, this is the third dominant. Now, as you go on the dominancy, this becomes much more noisy because the dominancy is lost. But the first dominancy is that the water should be trihedral like, which is very true, and the ship should be somewhere here, which is also true. You are able to find out coherent target on C with this is a coherent decomposition. I go to the incoherent one, the scattering factorization. In the incoherent one, I keep the same thing, no change at all. I just incorporate a volume scattering model. That's it. And since I know that I have this alpha, that's what previously, and I know that alpha between 30 and 40 degree corresponds to volume. And this is again can be proved from theory, from literature, that in this region you have volume model. If I use that, I can again do the same thing, no changing at all, very simple. It doesn't take a lot of time to compute, and I can find out again for this image what is the dominant. The dominant over the urban area is dihedrous. Over the water body, it is trihedral, which is true, which I've seen before. I'm getting it from here itself. And I'm getting the second dominant. The second dominant over the ocean surface is nothing but a cylinder of scattering. So, and now you go on and on, you start getting noisier. This is very important because what I'm trying to do is that I'm getting an image, no prior information. I'm trying to find out which part of the image has a dominant in the scattering. The dominancy over here is an even bounce, which is true because it's an urban area, which will show dominant. It's coming over here, hitting this and going back. So this will be all even bounces. The one which is the water will be odd. All odd bounces, single as such. Volumetric, those areas which are parks over here. Big parks with a lot of vegetation. Over here also vegetation. If I want to compute the power as it is done in many decomposition theorem given by from Freeman Durden to Professor Yamaguchi and so on, I can do the same thing over here. This is the power. Nothing but the power information, because here it was qualitative, here it is quantitative. You can find out what is the amount of power in the double bounce. What is the power in the surface? What is the power in the volume? You can find out easily from here. This is again the same thing. This is for the area of Mumbai. Mumbai, it's, as I said, over here is all urban area, which is true. Again, it's coming out to be even. This area, as I said, was a natural park. It's volumetric. It's green. These areas, if you see, are wetlands. These are all fresh, very clear wetlands. This is called a creek. The ocean goes in between those creeks, and there's a very thick wetlands are here. Very, very thick, and it's very like a forest only or something, but there's very water over here. So it's clearly found out over here. If you see the powers, like the powers over here are again over here the kind of a mixture of double bounce and surface, because it's composition of many things. So it's over here giving rise to something like a pink, not kind of a red, but because it's not pure double bounce. And here you can see they're all different kinds of shades of green over here, because there are different kinds of volumetric scattering up there. Again, this image of Allos 2, again, you see it's all urban areas over here. You see there's a problem again, this area. It is difficult to find out. But still, you are able to get something or the other. These areas again are urban area. If you see, you are able to find out again different parts of this one as an urban area. So this is similar to what is there in literature, where people do what is called as a model-based decomposition. There are many in literature. If you go into the pulsar literature, there are many of them which are there in decomposition. But here we are not doing any decomposition, but we are giving the same kind of information as it. The beauty of it is that over there, those models are restrictive models. You cannot go beyond 3 or 4 models, because it is not solvable. Because you cannot go on and on. So you cannot say that I have a 3x3 matrix. I break it up into 100 of them. I cannot solve it. It's not possible to solve it. I can only solve it now on putting constraints. That's what they do in decomposition, which is not the right way, because this putting of constraints is now constraining a lot of physical properties over here. Here, you don't have to do that. You give me as many models you want, it can be easily incorporated because it's a factorization. I'm just factoring the powers or the type, scattering type. So whatever number you give me the models, tomorrow you say, okay, I have a typical type of scatterer for which this is the model. I can put it over here. But if you give it to those people who have the scattering model, they cannot do it because it is hard bounded between using either a 3-component as done by Freeman and Durden, but now people are doing it 4-component, 5-component, little bit of 6. They're going on, but it's not the right way because it's constraining to find out the solution of a linear equation with a lot of constraints, which is not correct. Here, no constraint, nothing. You give me any model, I can simply input it. It's very, very flexible. This is again the Himalayan region. As you can see, except for this part which is surface-like, over here it's a very complex. It's complex with surface with many other things because it's snow over here. You cannot just judge them as such. If you see the scattering powers, you see again, as I said, the scattering power from this area, which is the forest, is actually surface-like. Over here, it's again a composition of surface and volume. Very complex to analyze these mountain-covered areas over here. I would like to have this done on some areas over here, if possible, on Rasa too. So because this is very important to see, because we cannot do all that kind of field work is not always possible over here. And this terrain is very, very difficult. We can only go up to here, maybe possibly. That's it. It's very difficult to go over there. After that, you cannot breathe me sometimes possible because it's too high over there. So I would like to maybe do the same kind of thing if it's possible with data sets which you have over here. It would be nice to see, and if we can have a time series, that would be wonderful to see that. If this is just comparison to see again this area of rice, where you have on May 2018 where rice was not there, in November where rice was there, you can see using the alpha GD, you can clearly see how the variation is. The variation over here is that this is surface-like because it's all watered over here. It's totally surface, very, very, very clearly. Here you have rice over here, it starts to be volume. Here. It's somewhere over here. I mean, it's not dihedral as such, but it's towards that, you can say. It's kind of a yellowish red kind of thing over here. So it's not the dihedral, but it's towards kind of dihedral. There's a stark contrast between them. So it can be easily used if you want to do a time series analysis. You can just put this parameter in time series and you can analyze them. It's wonderful because it captures the changes very, very well. If you see this again for the purity, you see it was purer over here because it was again nothing but water. Scattering was only one type of. As soon as you have rice with scattering is diminishing now. The purity has lost because you have something standing over here, scattering becomes more complex. So the purity is lost from towards one being something down. Helicity is difficult to characterize, but it gives some information, of course, when there is no and there is something. This is the classes, the segmentation. You can clearly segment that. Here, the segmentation was, everything was surface-like. The alpha was low and the purity was high. If you see over here, the class are all this kind of classes because it is all reddish over here, going towards the double bonds kind of thing, but with low purity kind of thing. But you can easily segment those areas, which is almost over here. Don't have to do anything at all, just with no prior knowledge, simply just the 2 parameters compared from here, which is just very easy work to do. And if you see over here, there is something over this is the Vijayawada urban area actually, which has also been captured over here in this class, which is constant. This is the city. This is the very, very densely populated big city There's some part on the top which is not come up. Yeah, the very very big, densely populated city on the river bank over here, and you can see this has kept over here, but this over here is all rice fields, the south of this. If you see again the dominant scattering type, the dominant scattering type over here is odd, of course. Again, the dominant scattering type over here is a combination now of even and helix. Because you've seen the helix was something over here. You see, there was nothing. There is something over here, not very high, but still. But you can see, the combination over here is the even and the helix, because it is hitting the thing and coming back, but there could be also multiple scattering between the stems, and possibly it could also happen by nature or by geometry, is that they could be separated by certain scale of the lambda which you are using. In this case, it is 5 centimeter, or that's at 2. So it possibly could create this kind of scattering. Also, it could make the linear polarization go circular, which is happening over here. It's natural. So it's a very complex scattering over here happening. Similarly, you can see the powers. Again, can be very well discriminating the area which is surface-like, the area which is double bounds, and kind of a mixture again, as I said. So summary over here is that the formulation is very easy, the framework. So you can do a high reproducibility. Interpretability is very high because you are just using models, and these models comes from literature. They are all there in the literature, and they all come from scattering physics, electromagnetic theory. These are all explainable kind of thing. No problem in that. So the interpretability becomes very high. As I said, it's very highly flexible because you can use arbitrary number of models. Tomorrow you give me another model which I have not used over here. It can be easily put in the framework, in the chain, without any problem at all. It's very flexible. Sorry, this one I have not talked about, but what happens in all these decompositions, as I said, is what they are doing. They are taking a covariance matrix, 3 cross 3, and this covariance matrix, since it has come, as I said, it has come from a spatial ensemble averaging. This is a full rank matrix. Now the idea is break up this full rank matrix into certain rank 1 matrices. Now you cannot go on and on doing it, the limitation of that. So the problem is that what they do, they develop kind of the way they do it, the trick they do it is that they compute one of those scattering, which is normally the volume scattering, and they subtract it from the covariance matrix. What is left is given to surface and double bounds. But the problem here is that when you make this volume scattering model from physics, nothing will be perfect model. So what you do, maybe you take out more power away from it, and there is something very little left to give it to either surface or to double bounds. So at the end, what you do, you come up with something where the power is negative, because you have to compensate somehow, because it's just an algebra. So you come up with powers which are negative, either in the surface or in the double bounds, which is absurd. Physics does not say power should be negative. And these people are trying, the people who have done a lot of work, including me, where to negotiate this negative power. But you can do to a certain extent, but not full, because of the fact that you are using a model from physics to say that this is my model for my target. But who said that this is a model for my target? It may not be. Tomorrow you say I have a model for a coniferous forest, I have a model for rice plant, tomorrow I have a model, because all of them will not work for everything. So maybe it works very well, but it may happen that you actually overestimate the volume. If you overestimate the volume, then there is very little power to give to the surface and to the double bounds, because the total power should be conserved. This case, you come up with negative powers, which is a very, very difficult problem to solve. People have solved it to a certain extent, but it's still not solvable. In this case, we have no negative power situation, because we are not doing decomposition. We are doing factorization. You give me as many of them, I'm just factoring it. So if I just factor them, there is no way that I'll be able to ever have a negative power. There is no question at all that there is no negative power over here. This situation is already gone. No overfitting. Option to be, as I said, there is no overfitting of anything because there's always an option of residue component. This is the use of similarity, geodesic distance in Canute space, which is highly tractable. This is nothing but this is on a space of 4x4 real matrices. Canute, they are real. Geodesic distance is well studied. So everything is like there, well known. So the tractability is very high. You can easily track what exactly has happened from the beginning when you have the data to your result. You can very well track everything what has happened in terms of your scattering. Similarity from a true metric, because this is a true metric at a geodesic distance, and this is a unique representation. So it doesn't make an ambiguity because the representation is very unique. Similarity with models, you can find out the dominance, as I showed that you can find out what kind of dominancy is there in the scattering model. And the approach to coherent can be incoherent. I can use the same model, same approach, or like the same framework, as I say always, that I can see the same framework for both coherent as well as incoherent decomposition or factorization, because it is not there in literature. People who are working on incoherent do not know how to approach the same problem in incoherent, because the scattering has changed. When it was coherent, it was okay, but now when you mixed up things by doing an ensemble averaging, but that means you go from an S, as I showed before in the beginning, from an S to a T or C or K, the mechanism has changed. Before it was scattering from this one, now this pixel contains this, the mixture. Now I do not know how to apply the same thing over here because I was only knowing how to apply this on a target. So there's a problem. But here you don't have to do that, because here it only depends upon the model. So any model you take, you can do a coherent approach and an incoherent approach at the same time. So it's very universal. Don't have to bother about, oh, I go and do a coherent decomposition given by XYZ. If the data is coherent, if the data is incoherent, then I go into something else. No. Just one thing can be done under this umbrella. So that's all it is, and we have our collaborators from University of Rennes, Professor Potier. We have from FBK, where David was there with Francesca and also with Lorenzo. In Trento, we have from Professor Freddy from the University of Federal de Alagoas in Brazil, Maceo. Professor Juan Lopez Sanchez from University of Alicante, who is helping us a lot with the crop analysis for the vegetation thing. With the DLR, I have a collaboration with Professor Mihai Datcu, because I do some part of deep learning, but I'm not a deep learning person. But we have people who are working on deep learning using pulsar data, mostly on retrieval kind of work, which is done with Professor Mihai Datcu with collaborations. I have a student who is actually collaborating. Yeah, who is collaborating with him over here. We have a good collaboration with Professor Gamba from University of Pavia on the urban studies. So he is looking after all our studies with urban, and there's a new proposal which we are working along with Professor Gamba. We have worked with Agriculture and Agri-Food Canada with Dr. Heather McNaren. She's working a lot with us on the Radar Set 2 campaign, and also the upcoming Constellation mission, which will be there for both full pole and also compact. There will be a lot of time series data available. I was talking to Abdul on that day, so this will be a lot of availability of time series data for agricultural application. That's the thing, because they are only doing a lot of agricultural application for different parts of the globe, and they have also one test site in India. They are doing it, which is the Vijayawada area. So now we have to focus a lot on that. With Natural Resources Canada, CCRS, I have a collaboration or work going on with Rida, with some newer methodologies along with him. So this is all what we have, and a possible collaboration with Emmanuel, of course, over there going on, others. Thank you very much for your time and patience.